Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. We have reached on the lecture 7 of solid state. Till now, we have discussed everything about crystalline solids. How are crystalline solids? How can we classify them? We actually discussed basically about the cubic crystal systems, different types of arrangement of atoms in a crystal system. We have discussed a lot about it. We have also discussed the layering, which is a very important and very conceptual part. If you're not clear, you definitely have to go through the last lecture. That is the most important lecture. I have showed you a video there, the animation, how layering actually happens in the solids. Okay, yes. So today we will be covering about, now we have discussed everything about crystalline solids. Now, my dear students, we always think that, yeah, crystalline solids will be absolutely perfect crystals, right? Yes, but they also have some defects and we are going to discuss about those defects. Okay, why do defects arise in solids? What is the basic reason behind them? Today, we will be understanding about that and we'll cover everything about the solid state today. Okay, my dear students, so let's start the session. So if you talk about the solid defects, my dear students, solid defects can be of different types. It can be a point defect. I can say that a solid defect can be a point defect. That is a defect at one particular point of a solid, right? Yes. The other thing could be that it is a line defect. Might be some line in a solid is completely defected, then it will be known as a line defect. And the third type would be your plane defect. When the complete plane has some defect in it, that is known as the plane defect. Okay, but we will be majorly discussing about the point defects. Point defects are in your syllabus. So today we will be covering all about that. I hope all of you are excited. So let's start the session, my dear students. So let's talk about the defects. So why do defects arise? The first and the most important question. And when are solids absolutely perfect? See, my dear students, let's talk about you. You are sitting in a room and you are completely stable. You are in your relaxed position. You don't have any issues till now. Okay. All of a sudden, what happens is a spark comes and somewhere you see some fire. Okay, in the particular room you are present. Okay, what will happen? You were in your stable position. Now you will gain some energy and you will just rush out of the room, right? Yes. So you saw the fire and you gained some energy and you rushed out of the room. Similarly, your solids are absolutely perfect and their stable positions when they are at absolute zero temperature, that is 0 Kelvin temperature. Now, as you start giving some temperature to your solids, your solids actually start showing some defects. Okay, yes. So this is the major case why defects arise, because of increase in temperature. Okay, one by one we'll read everything about it. The first thing is this. Okay, it is stable at absolute zero. It shows some defects when the temperature is, when you heat a solid. Okay, perfect. Next, my dear students, all the solids are still stable. Why are they stable? Because they will be stable as long as their electrical neutrality is maintained. As long as the electrical neutrality of a solid is maintained, it is stable, completely stable. Okay, so now let's understand this. The irregularities in the structure of crystalline solids is known as solid defects. Okay, the irregularities. It should be irregularities. The irregularities in the structure of crystalline solids is known as the solid defect. Okay. At 0 Kelvin, that is O and K, you can call it like OK or you can say 0 Kelvin. The crystal is perfect and there is no solid defect because it is in its most stable form. Okay, now the extent of solid defect increases with the increase in temperature. As you will increase the temperature, the defect would increase. If any solid defect, it should be in any solid defect, electrical neutrality will be preserved. Always and always, your total positive charge would be equal to the total negative charge. That is something very, very important. Okay. Yes, we will always keep in mind that if we are talking about a solid, its electrical neutrality should be maintained. So this is very, very important case for us to understand. In fact, all the points are very important. So please note them down. You be using all these points in the defects, and then we'll move forward. I hope you've written it, my dear students. Now, the constituent particles may not be present at exact lattice points. Now, what happens is, what actually happens in a point defect is, might be there is a point where your constituent atom was actually supposed to be present, but it will not be present there, and that would be the point defect. Okay, I told you in point defect there would be a defect at some point. And how can it be that an atom was supposed to be present there, but it is not present there? Why is it not present there? Because it is a point defect, right? Yes. So this is the basic idea behind a point defect, that the constituent particles may not be present at the exact lattice point. Okay, perfect. Please write it down, then we'll move forward. Now let's try to make a small flow chart that what kind of defects we will be discussing today. Okay, so now, my dear students, if we talk about the solid defects, defects are majorly classified as two. It is stoichiometric defects, and the other is non-stoichiometric defects. Now let's try to understand what stoichiometric defects and non-stoichiometric defects denote. See, you have a particular ratio of your cations to anions, right? Yes, you have solids, you have cations and anions. So you have a particular type of cations and anions ratio, right? Yes. If that ratio is maintained, then it is a stoichiometric defect. If that ratio is not maintained, then that is a non-stoichiometric defect. I'll give you example, you'll understand. Let's first understand this particular point. Now, my dear students, your stoichiometric defects can be in two major parts. The first part could be, also there is one more type of defect which is also known as impurity defect. Okay, it is impurity defect. Now let's try to understand the stoichiometric defect. So if we talk about the stoichiometric defect, my dear students, your stoichiometric defects can be present either in non-ionic solids. I could say these are your ionic solids, or they might be non-ionic solids. Now, if we talk about non-ionic solids, they will not have cations and anions individually, right? Yes. Here, my dear students, the two types of your defects are classified as vacancy defect and interstitial defect. Okay, now let's talk about ionic solids. Now, if we talk about ionic solids, my dear students, then ionic solids can be classified majorly as two again. The one would be your Schottky defect. Please mind my spelling of Schottky. Okay. I don't remember its spelling. It's okay. I am not an English teacher, by the way. Okay. And Frankel defect. We'll study each and every one of it individually. Now, these are the defects which maintain your stoichiometric ratio. That is, cations to anions ratio will be fixed. Okay, now let's talk about non-stoichiometric defects, because impurity defects are they are in their way one individual. Now let's talk about the non-stoichiometric defect, where the cation to anion ratio changes, and now, my dear students, they can be classified as either metal excess defect, or they could be metal deficiency defect. Okay, so these are the types of defects that we will be discussing in this particular chapter. We'll be discussing each and every defect one by one, so you have to just you'll have to be patient. Okay, yes, so let's start. Please write it down. Okay, now let's try and understand point defect. Point defects are majorly classified as a stoichiometric defect and non-stoichiometric defect. This is written stoichiometric and this is written non-stoichiometric, just in case if you're not able to see it. Okay, so this is your stoichiometric defect, non-stoichiometric defect. I have made you draw the complete flowchart, so it is of no use here. Now let's talk about the stoichiometric defect. What exactly is meant by stoichiometric defect? In this defect, the stoichiometric formula remains unaffected. That is, the ratio to your cation and anion always remains the same. Okay, yes, that is something very important. You can write that ratio of cation to anion remains same. Okay, now let's talk about the non-stoichiometric ratio, stoichiometric defect. The stoichiometric formula, that is the ratio of the ions, that is the ratio of your cation to anion, will be affected. So, ratio of cation to anion is changed. Okay, so it gets changed, then that would be known as your non-stoichiometric defect. Okay, I hope till now everything is very clear. It is very easy. Please write it down and then we'll move forward. Okay, now we will be discussing the stoichiometric defects first. Okay, before discussing the stoichiometric defect, let's discuss about the defect. Let's discuss about the non-ionic solid defects. Okay, they are majorly classified as vacancy defect and this is your vacancy defect, and that is your interstitial defect. Now let's try to understand it. Okay, so now, my dear students, if we talk about the vacancy defect, what actually happens is, let's say you have a solid like this. Okay, so since it is a non-ionic solid, there we will not discuss about the charges, right? Yes, it is a non-ionic solid. So let's say you have A here, 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 and A here. Okay, so now what happens is, in this particular solid, what happens is, you heat this solid and obviously it will have some defect here. So when you heat this solid, what happens is, let's say your one of the A goes away. One of your A goes away. Okay, yes, since it is a non-ionic solid, we will not see any ratio or anything. What will we say? Now here, ma'am, since A is gone, there is a vacancy present. So since here only a vacancy is present, we call it a vacancy defect. We call it a vacancy defect. Okay, this is something written in your NCERT. That is the reason I am explaining you this. This is of no use. Generally, questions are not asked from this part, but still it is there in your NCERT, so I'm just explaining you. In non-ionic solids, my dear students, on heating a solid, a vacancy is created, and that particular defect is known as a vacancy defect. Simple, a vacancy is created, so it is known as a vacancy defect. Now let's talk about the interstitial defect. From interstitial defect, I hope now you can imagine what would be a interstitial defect. Now, if you talk about the interstitial defect, let's say you have A here. Now, you did heat this particular solid, and what happened? And what happened, my dear students? One of your A occupied this interstitial position. Now, A left its position but it came to its initial position, to its interstitial position. So this is the interstitial site. Interstitial site. Okay. So to this interstitial site, A is written, A comes here, and that is the reason it is known as an interstitial defect. In an interstitial defect, a atom leaves its position and occupies a position in its interstitial site. Okay, so this is how you define an interstitial site. It is very simple, very easy. I don't think so there is any issue till now. Okay, but you got an idea about from these what are we going to discuss in ionic solids. Okay, I'll just make you understand. Don't worry. First write it down and then we'll move forward. If you want to write it, you can write a vacancy is created. And if we talk about interstitial site, atom occupies the interstitial site. Okay, yes, now write it down. I hope you've written it. Now let's move forward. Now, my dear students, now is the main part coming from where generally questions are asked. If you talk about your stoichiometric defects, that is now, my dear students, we are talking about the ionic solids. Okay, so now we are talking about the ionic solids, and in ionic solids you have cations and anions. Okay, so you can classify the stoichiometric defects as Schottky defect. Okay, or you can classify it as Frankel defect. These are the two types of defects that arises. Okay, I hope you're clear with this, Schottky defect or the Frankel defect. Now, let's try to understand what Schottky defect and Frankel defect do. Okay, so now, my dear students, I'll make you understand here and then I'll make you write points together as well. So let's say you have a solid like this. Since it is an ionic solid, definitely you'll have, definitely you'll have A plus, B minus, A plus, B minus. Okay, so here it will come B minus, A plus, B minus, A plus. Okay, yes. So now what happens in Schottky defect is that, let's say your one of the cation, since you know that cations are smaller in size and your anions are larger in size, because in cations one electron is left, whereas in anions one more electron has came in and the size has become even bigger. So cation size is generally less, so one of the cation just leaves the site. Okay, so now when your cation will leave the site, my dear students, what will happen? Just a second. Huh? So now what happened? Oh, okay, I am sorry. We did discuss this. Where is it? Yeah, it is here. Yeah, it's fine. I don't know what happened. Everything written is gone. Okay. What's happening? Okay, I'll draw it again. I don't know what happened here. So you have atoms like these. Okay. So now, since it is an ionic solid, you will have A plus, B minus, you will have A plus, B minus, you will have B minus, A plus, and you will have B minus, A plus. Okay, so now what happens in Schottky defect is that, my dear students, what happens in Schottky defect is that one of your cation leaves it. Now you'll heat the solid, one of the cation, since it is smaller in size, it is easy for it to leave. So what happens, what is happening? What is happening, yaar? I don't know. What's the issue? Fine. I'll make you understand on the next slide. Okay, so now let's talk about the Schottky defect, and once and for all, I am drawing it again. Okay, I am sorry, my dear students. So you have Schottky defect. Now what happens in Schottky defect? You have atoms like these, sorry, positions like these, and your ions occupy these positions. A plus, B negative, A plus, B negative. B negative, A plus, B negative, A plus. Okay, so now what happens is you'll heat the solid and obviously some defect will take place, and what happens is one of your cation leaves the position because cations are smaller in size, so it is easy for them to leave. So this is how a vacancy is created. Okay, now this is a defect, and that is known as Schottky defect. Okay, and how can you remember this? Since the word is Schottky, can you remember this word with short? It is short of some ions. It is short of some ions, that is, it has lesser number of ions. Okay, which defect has lesser number of ions? Schottky, because ions leave their positions. Now, if you see the total positive charge here, you will say 1, 2, 3. Ma'am, total 3 positive charges present. Can I ask you how much of the negative charge is present? You say 1, 2 and 3. 4. Ma'am, 4 negative charges present here. Now, my dear students, I told you that be it anything, every time your electrical neutrality will be maintained. Right? Yes. Now, for the electrical neutrality to maintain, you need 3 negative charge and not 4 negative charge. So what happens is when one A plus leaves, one of the B negative also leaves because it has to maintain the electrical neutrality. And now if you see, you will say that you have 3 negative charge and you have 3 positive charge. So there is electro neutrality. This is something just to explain you. Okay, this is something just to explain you. It's not only 3 positive and 3 negative charge, just an example to make you explain. Okay, so now my dear students, what happens in Schottky defect is equal number of cations and anions leave their sites. Equal number of cations and anions leave their site. And now if you will see the ratio of cations to anions, what will you see? You have 1, 2, 3 cations and you have 3 anions. So the ratio is 1:1. And if you talk about initial, if it was here A plus and B minus, still you had 4 cations and 4 anions, still the ratio was 1:1. And that is the reason it is known as a stoichiometric defect, because the ratio of the cation to anion before the defect and after the defect is exactly same. Okay, yes. So this is what actually happens in a Schottky defect. I hope you are clear with the Schottky defect. Okay, now let's try to understand what is a Frankel defect. Okay, so what happens in a Frankel defect, my dear students? You have atoms like these positions which are occupied by cations and anions. So now your cations and anions will occupy position. Let's say A plus B minus, A plus B minus. You have B minus A plus and B minus A plus. So now what happens is in Frankel defect, my dear students, one of your cation leaves its site. Now what this cation does is, this cation occupies some interstitial position in the solid. So it left its position and it occupied some interstitial position. Okay, so now if I ask you initial cation to anion ratio, can you tell me 1, 2, 3, 4? You will say, ma'am, 4:4. Yes, so it was 1:1, right, initially. Now after the defect has arisen, after, my dear students, what will happen? You will say, still ma'am, it is present in the solid, so still the ratio is 1:1. So since the cation to anion ratio isn't changing, it is a stoichiometric defect. Now let's see whether the total electroneutrality is maintained or not. You have 4 positive charge and you have 4 negative charge. So yes, electrical neutrality is also maintained. Electrical neutrality is also maintained, right? Yes. So this is the major difference between your Schottky defect and Frankel defect. In Schottky defect, equal number of cations and anions leave their sites, whereas in Frankel defect, a cation leaves its side and occupies some interstitial position. Or you better say ion, any ion. It could be cation or anion. Majorly it is cation, but any ion leaving its interstitial site, its site and occupying the interstitial position is known as a Frankel defect. Okay, yes. So first draw these diagrams because we'll be using these diagrams a lot, and then we'll move forward. Okay. Perfect. I hope you've written it. Now see, they have drawn diagrams for you as well. I have drawn it on my own, so let's just leave it and let's try to understand each and every difference, because question is generally asked on Frankel and Schottky's differences points. Okay, so we need to understand each and every point very seriously. The first point says that in this defect, equal number of cations and anions are found to be permanently missing. They are permanently missing, but your number of cations and anions are exactly equal, and that is the reason electroneutrality is still maintained and the cation to anion ratio is also same, and that is the reason we call it stoichiometric defect. Okay, short. I'll write short so that you will understand always and always that Schottky defect is short of atoms. Okay, let's talk about the Frankel defect. In this defect, the ions are dislocated. They are dislocated from their lattice site and they are found to be present in the interstitial positions, and they are found to be present in some interstitial position, and they are found to be present in some interstitial site. Okay. Perfect. I hope you're clear with this. Very good, my dear students. You can write it down and then we'll move forward. Let's discuss another point. I hope you've written it. Now, since, my dear students, in Schottky defect, you know that equal number of cations and anions are leaving, and the mass is due to the cations and anions only, right? Yes. So if I talk about If I talk about density, it is mass by volume. Okay, so volume is for the lattice point, right? Yes, for the lattice, cubic lattice. So volume will not change, it will remain constant. Okay, ma'am, volume will not change, it is constant. But if we talk about the mass is because of the ions present. Mass is because of the ions present, my dear students. Now what is happening? Your two of the ions are missing. This means that, ma'am, mass is decreasing, and since mass is decreasing, your density will definitely decrease. So this is the defect where density actually decreases. So what will we say? Density decreases due to the Schottky defect. Now let's talk about the Frankel defect. If we talk about the Frankel defect, in Frankel defect we had ions present like this. Let's say you had A plus here, B minus here, A plus here, B minus here, B minus here, A plus, B minus, and A plus. Now one of it just left and it occupied some interstitial position. Let's say A plus. Okay, now can I talk about the density here? Yes, please, let's talk about the density. Density is equal to mass upon volume. Now volume is constant, that is understood, because the cubic crystal system will remain the same. Okay, now let's talk about the mass. Mass is because of the ions. Has there been any change in the number of ions? No, it just changed its position, but the number of ions are still the same. And since they are same, your mass will also be a constant value, and eventually your density of the crystal system will also be constant. So can I say that density remains same? Yes. In Frankel defect, my dear students, density remains same because no ion is leaving the lattice sites. Okay, perfect. I hope you are clear with this. Please write it down and then we'll move forward. Now let's talk about the other point. It is found in compounds having high ionic character and high coordination number. Okay, what does it say? It says that the Schottky defect is found in the compounds having high ionic character and high coordination number. Okay, now this is something very important, my dear students. When we talk about the octahedral voids, generally octahedral voids have a larger coordination number, that more of the atoms are present there. Okay, since no ion is occupying the interstitial position, this means that the void space is very less. This means that it has a high coordination number. So high coordination number atoms actually show the Schottky defect, whereas low coordination number atoms show the Frankel defect. Okay, yes, this is something very important. Please write it down and then we'll move forward. I hope you've written it. Let's talk about the other point. Now, anionic and cationic sides. Now, my dear students, just imagine why in Frankel defect the cation was able to occupy the position in the interstitial site. Obviously, it had a very small size, and that is the reason there was a very large gap in the voids. That is the reason your small cation went to the void and occupied that position. But such void size was not available in Schottky defect. That is the reason they had to leave the site. Yes. So can I say that the difference between the cation and anion size is larger here? Eventually, there is more position available at the interstitial site as compared to your Schottky defect. Yes, my dear students, the size of cations and anions are not comparable because there will be very high extent of polarization. Their size gap is very much large. That is, size of cation and anion has a large difference. Okay. And if you talk about the anionic and cationic sides here, my dear students, they are comparable. So size of cations and anions are comparable. Okay, I hope it's clear. Perfect, my dear students. Please write it down and then we'll move forward. Now, this was all about your stoichiometric defect, that is your Schottky defect and Frankel defect. Okay, generally questions are asked whether that which of the following is the one where density doesn't change. Where density doesn't change? Frankel defect. Reason you know, very good. These are the few things that you need to remember. One example that you need to remember is AgCl. Okay, AgBr, sorry. AgBr is such a compound which shows both of the defects. It can show Frankel defect as well as your Schottky defect. So this is an example which you need to remember. Okay, because question will be asked from this particular part only. Okay, I hope you've written it. Now let's move forward. Next topic is, my dear students, your non-stoichiometric defects. Now in non-stoichiometric defects, what actually happens is, in non-stoichiometric defects, the ratio of cation to anion will definitely change. Okay, if it is changing, this means that you have a cation and you have an anion. We call cation as metal. Either the metal will be more or the metal will be less. These are the two cases which can happen. That is something we have written, that in non-stoichiometric defect, metal excess defect can be either okay, we have talked about metal excess defect first, and then we'll be discussing about metal deficiency defect. Okay, now how can metal excess take place? Ma'am, either you have added more of the metal to it, or ma'am, the existing metal just left its position and you got the metal excess defect, right? Yes. So majorly your metal excess defect can be one due to anionic vacancies, Okay, let's say you had some metal Mx1 and then minus, you had some lesser amount of the ions. Maybe some ions just left and you got more of the metal. Okay, yes. or it could be incorporation of metal, or it could be incorporation of metal. That is, you had some metal, you added some, and then you had your anion. So how can a metal be in excess? A metal can be in excess in two parts. Either you have added more of the metal to it, then you had a metal excess defect, or some of the anions just left the site, and that is the reason you had some anionic deficiencies and you had more of the metal, and you said that it is a metal excess defect. So metal excess defect can happen because of two cases. Either you add more metal, you remove the anions present. Okay, yes, now we'll be discussing both of the cases together. So now when we talk about the cases, please write it down and then we'll move forward. Let's talk about the anionic deficiencies first. Okay, anionic deficiency. Now if anionic deficiency is there, this means that you had some mx ionic metal and you had this one, and some x amount of it is gone. Okay, so now let's try to understand how anionic deficiency takes place. Okay, let's say you have a metal. Let's say you have a metal. Let's say you have a solid, in fact, and the solid is NaCl. So you have Na, you have Cl, you have Na plus, you have Cl minus, you have Cl minus, Na plus, and you have Cl minus, and you have Na plus. So now, my dear students, what actually happens is you have a metal crystal, you have a crystal system like this. Okay, now you pass some Na vapors through it. Okay, now you pass some sodium vapors through it. This solid, you pass some sodium vapors. Okay, now when you will pass some sodium vapors, what will happen, my dear students? Your sodium your sodium will lose a electron. It will give you Na plus and 1 electron. Why? Because sodium has a tendency to lose electron. Sodium has a tendency to lose electron. It only wants to lose electron and gain the stable noble gas configuration. Okay, so when you pass sodium vapors through this solid, sodium tends to lose an electron and convert it into Na plus. Now, my dear students, what happens is this Na plus wants a friend which is Cl minus, because they both are best friends, right? Yes. So when it passes through it, it sees that it has some Cl minus here. So it says to the Cl minus that let's just go away from here. Okay, so this Cl minus says, okay, fine, you're my best friend, obviously I want to go with you. So they just go together, Na plus and Cl minus, and you get NaCl, right? Yes. And since your Cl minus has left, you get a vacancy here. You get a vacancy here. So now if I see the total number of cations and anions ratio has been changed. You have 4 of the cations, but you only have 3 of the anions. Also, you have 4 plus charge and you have only 3 minus charge. Okay. So now the problem has arisen because we need electrical neutrality. We really want electrical neutrality. Without it, we cannot do anything. What will happen now? Now, my dear students, comes the entry of the superhero. What does the superhero do? Here is your superhero, electron negative, right? Yes. What does this electron do? It just goes here and occupies this position. Now, electron was the savior, because this whole solid just wanted a negative charge to maintain its electron neutrality. Now, if you see, you have total of 4 positive charge and total of 4 negative charge. So, the electrical neutrality is maintained. But if I ask you the ratio of the cation to anion, initially it was 4:4. That is 1:1. But now you have 4 of the cations but only 3 of the anions Cl minus. So the ratio is changed, and that is the reason it is known as a non-stoichiometric defect. Now it is a non-stoichiometric defect. The electron has saved the day, my dear students, and that is the reason this particular part is known as F center. It is known as F center. Now let's try to understand what does this F center mean. What does this F center mean? What is the role of this F center? It has a very, very, very important role. See now, my dear students, your F center is the very, very important part. Generally, questions are asked from this particular part. You know that you have a single electron present, that is, you have a unpaired electron present here. So now we'll be understanding and talking about the F center part. Actually, this F center part actually imparts color to the solid. You see solids different colors, that is because of this F center present. I'll make you understand how. Before that, write it down, all the part that I have made you understand, and then we'll move forward. I hope you've written it. Now see. F center, the unpaired electron occupying the lattice site of the anionic vacancy is known as the F center. So what is the F center? Which occupies the anionic vacancy, which saves the day. Okay. Next, the unpaired electron in the anionic vacancy F center gives rise to paramagnetism. I hope all of you have studied what is paramagnetism. When does paramagnetism arises? It arises when there are unpaired electrons present, and in F centers there is a unpaired electron, so paramagnetism arises. Perfect. Yes, please write it down and then we'll move forward. I hope you've written it. Now, the F center is responsible for the color of the crystal. The F center is actually responsible for the color of system, but how is it possible? Now try to understand it. Let's say you have an electron present here. See now, my dear students, you know the electrons are very stable. Okay, they are present in their most stable state. Now what happens is these electrons get excited to the higher energy level. They go to the higher energy level. They enjoy. Whenever you talk about your friends, you feel very energetic when your mother says you that we are going to your friend's house or anything. You'll go to their house, you'll play, you'll enjoy, but eventually you want to come back to your house at the end of the day. Same way, my dear students, electron gets excited and it goes to the higher excited state, and then it wants to come back to its original house. Now, there is an energy difference here. Here, he was in very high energy, but here, it is in its most stable position. So, in order to come here, it needs to emit the extra energy, and it emits the extra energy in the form of light, and this light actually gives you the color to the solid, and this light gives the color to the solid. Okay, yes, so the F center is responsible for the color of the crystal. On excitation, now your electron got excited, the electron goes to the higher energy level, it went to the higher energy state. When it comes back, it gives rise to the emission spectra, and this is your emission spectra, because of which we see the color, and that is the reason your NaCl solid seems to be yellow in color. Your NaCl seems to be yellow in color. Okay, perfect. Please write it down and then we'll move forward. Now, when potential difference is applied, now you have an unpaired electron. Whenever you will apply a potential difference, the F center can move in the same direction, giving rise to little electrical conductivity. Hence, negative charge is moving. It is called a N-type semiconductor. Okay, I'll make you understand the semiconductor part in those electrical properties when I'll make you understand the electrical properties. But you can understand that since it is a single electron, it is a free electron, so it helps in movement of charge, and that is the reason it is known as a N-type semiconductor. Okay, please write it down and then we'll move forward. I hope you've written it. Now let's move forward. Okay, yes, so this was all about how the deficiency of anion can cause a defect, and it can eventually increase the metal's amount. Okay, so we can say it as a metal excess defect because of the anionic deficiency. I hope it's clear till now. Now, the next type of metal excess defect could be your incorporation of metal. You might add extra metal to a solid. How can this happen? Okay, so let's see. Let's say we have a solid. Let's say we have a solid here like this. Okay. Now, I have, let's say, I am talking about ZnO. Okay, I have a solid of ZnO. So I have zinc 2 plus here. I have O2 minus here. I have Zn2 plus here. I have O2 minus here. Zn2 plus O2 minus Zn. Oh, sorry. Right, yes. So you have O2 minus here, you have Zn2 plus here, you have O2 minus here, and you have Zn2 plus here. If I talk about ZnO, I know that I have Zn2 plus. I have 2 electrons present here, right? Yes. So now, my dear students, what happens is sometimes in a solid, you get, let's say you have this zinc oxide present here. What does this do? It just goes into this side and Zn occupies this interstitial position. So your Zn2 plus has occupied the interstitial position, and the left 2 electrons go and occupy the other interstitial position. So in a particular ionic solid, your cation as well as the corresponding number of electrons go and occupy the interstitial position. Now, if you see, my dear students, initially you had zinc 2 plus ions. Total, how many? 1, 2, 3, 4, and you had O2 minus 4. So the ratio was 1:1, and the stoichiometric ratio was also maintained, and electrical neutrality was also maintained. Now, if you incorporate a metal, which is, let's say we have incorporated zinc 2 plus. Now, if I talk about Zn2 plus and O2 minus, now you have 5 Zn 2 plus and you have 4 O2 minus. So the ratio has changed, and since the ratio has changed, can I say that it is a non-stoichiometric defect, and is it electrically neutral? Yes, total of positive charge is 1, 2, 3, 4, 5, 10 positive, and you have 10 a negative charge. So yes, ma'am, electrical neutrality is still maintained, right? Yes. So the electrical neutrality part is good to go, and the ratio has changed, so it is a non-stoichiometric defect. Okay, so it is written that a metal enters at the interstitial site as a cation, and the free electrons are left another interstitial site. It is neutral. It is a neutral type of semiconductor. It is a neutral type of semiconductor. Okay, because it has free electrons, so it can conduct electricity, and that is the reason we are calling it a semiconductor. And since it has free electrons, so it is known as a N type of semiconductor as well. Okay, yes, I hope you're clear with this. You can write it down and then we'll move forward. I hope you have written this, my dear students. Now let's move forward. Now, this is the only one defect, my dear students. If I talk about the density here, can I say that it is mass upon volume and the volume remains constant? Right? Yes. Now let's talk about the mass. Mass. See, you have masses of the ions, sum of the mass of the ions. Initially, you had the mass of 4 Zn2 plus and 4 O2 minus. But now you have the mass of 5 Zn2 plus and 4 O2 minus. So, can I say that mass has increased? And since mass has increased, the density has increased. And this is the only one defect where the density actually increases. This is the only one defect where actually density increases. And generally, the question is asked that which is that defect where density actually increases. It is your incorporation of metal. So it is very important because question will definitely be asked from this particular part. Okay, let's see. Metal excess defect of this type leads to an increase in density. Only defect where density increases. So this is something very important. Please write it down and then we'll move forward. Now let's talk about the other defect, which is metal deficiency defect. Now what if metal is deficient, and how can this happen? How can metal be deficient? Now let's try to understand that. See, my dear students, let's say I have a solid like this. I have a solid like this. And it is Fe2 plus, then I have O2 minus, then I have Fe2 plus, then I have O2 minus, I have O2 minus, Fe2 plus, then O2 minus, and then Fe2 plus. Okay, so now my dear students, I know that Fe has a tendency to show two different oxidation states. It can be present in Fe2 plus or it can be present in Fe3 plus. So it has a tendency to show variable oxidation states. Okay, so now what happens is, let's try and understand what if my dear students, I change this Fe2 plus with Fe3 plus, right? Yes, and also now I change this Fe2 plus with also Fe3 plus, right? Yes, so now I have 3 plus 3 6 7 8 9 10 10 of the total positive charge. No, there is something wrong with it. I have 6 7 8 9 10 10 positive charge. I have O2 minus here, I have O2 minus here, I have O2 minus here, 8 to negative charge. Okay, so now I'll have to increase it to make you understand. So let me just increase the atoms. Okay, so now I have 8 negative, so I need O2 minus here as well. I need O2 minus here as well. Then I'll not have Fe2 plus here. Then I'll have Fe. Then I'll have O2 minus here and Fe2 plus here. I hope now the total charge is balanced. This is balanced. This is 3 plus charge. This is 10 and this is also 10. Yes. Okay. So now see what happened is, now if you see my dear students, initially when you only had Fe2 plus, you could say that the ratio was exactly equal. The number of Fe2 plus were exactly equal to Fe2 minus, right? Yes. But since Fe can also show you Fe3 plus oxidation state, some of its ions starts showing Fe3 plus oxidation state. Now in order to maintain the electroneutrality, obviously one of the O2 minus has to leave, and now my dear students, the ratio of the cation to anion has changed, but the electroneutrality is still maintained, because that is the most important thing, right? Yes, and that is the reason it is known as a metal deficiency defect. So which metals do show the metal deficiency defect? Now, metal deficiency defect is only and only shown by the metals which have a tendency to show variable oxidation states, Okay, so this defect can exist where the metal has the tendency to show variable valency. The positive charge lost by the missing of the cation is compensated by the higher valency cation which are present in the metal, and that is the reason we say that metal is comparatively less as compared to the anion, right? Yes, perfect. So this is how we show the metal deficiency defect. Okay, I hope you're clear with this. Please write it down and then we'll move forward. Now we will try to understand that how can we find that how much of the vacancy will take place. Okay, so now my dear students, how will you imagine that? Now let's say you have a metal, let's say you have 3 Fe2 plus, here also Fe2 plus, and here also Fe2 plus. Okay, so now my dear students, if I again write these, and now I want to relate them. Let's say I had Fe3 plus, I had Fe3 plus. So can I say that these three are equivalent? I have 3 Fe2 plus ions, and if I replace the Fe2 plus with Fe3 plus, I can say that it is equal to 2 Fe3 plus plus 1 vacancy. So my dear students, each Fe3 plus ion creates a vacancy. Each Fe3 plus ion will create a vacancy, right? Yes. So 3 Fe2 plus is equivalent to 2 Fe3 plus plus 1 vacancy. Okay. Yes. So this is how we relate the number of vacancies. I hope you're clear with this. Perfect, my dear students. Please write it down. Written? Perfect. Now just see. Number of cationic vacancies present in 1 mole of doped lattice is equal to the, you have to relate both of the valencies, you will have to relate both of the vacancies and find out how many vacancy does a particular ion create. Okay, perfect. Please write it down. Now let's try to solve a few questions. Okay, now the questions are, okay, we'll solve questions in the next class, so just wait a second. Yeah, we'll solve the questions in the next class, my dear students. Till now, let's keep it here. We'll solve a few questions in the next class. So now what is your homework for today is that you'll have to read the NCERT of all these defects, because only and only questions will be asked from these defects. I have not discussed any of the questions today, so I'll discuss the questions in the next class. Starting first, we'll discuss the questions and then we'll cover our magnetic properties and electrical properties. Okay, yes, I hope you're clear with this. Please do read the NCERT, read the NCERT of the electrical and magnetic part as well, so that you will have a better understanding when I'll make you explain everything. Till then, my dear students, keep studying. We'll meet in the next session. Thank you so much. Bye bye, take care.